Hello and welcome back to my series called The Added Edge, which is to give you additional knowledge to augment your understanding of the H2 syllabus and help you score even better for H2 chemistry examinations. So today's topic is ARIO rules to determine stability of anions. So ARIO is basically an acronym. So it stands for the factors that determines the stability of a particular organic anion. So why is today's topic important? Why is determining the stability of anions an important thing? So this is because it has a big factor when it comes to evaluating strength of organic acids. Remember, the more stable the conjugate base A minus, which is an organic anion, the stronger the organic acid HA. Right? So let us dive straight into it and see what are the factors affecting the stability of anions. Firstly, A is and by the way, from the first factor stated is the most important, so A is the most important, and O is the least important. So the first factor is atom, or more specifically, the atom bearing the negative charge. So if the two atoms are from the same period, the dominant factor is electronegativity. And the concept here is that the more electronegative atom is better at bearing a negative charge. So for example, let us take a quick look at two examples. So the first would be this anion here, right? The ethyl anion, and then the next would be this anion over here, right? The methoxide anion. So what is the key difference over here is the atom bearing the negative charge. For this it is the carbon atom, and for this it is the oxygen atom. And so note that oxygen and carbon are from the same period, but the oxygen atom is far more electronegative than the carbon atom, and thus the negative charge is better held on the oxygen atom in the methoxide ion than on the carbon atom in this anion over here. So we thus can conclude that the methoxide anion is the more stable anion here. And so if the two atoms, sorry, there's a typo here, if the two atoms are not from the same period, sorry, I forgot to include a word, are not from the same period, the dominant factor is the size. So a good example would be an alcohol versus a thiol. Or rather, let us compare the conjugate base. So oxygen and sulfur, right now they are from different periods, and sulfur is a larger size, and normally the larger the atom bearing the negative charge, the more able it is to stabilize the negative charge, because the negative charge will be dispersed over a larger region of space, right? And so allowing a greater stabilization of the anionic species. And so this is thus the reason why thiols are generally more acidic than alcohols, because the conjugate base is more stable. So the second factor, I put it in blue over here because it's something we learned already in the H2 syllabus, is resonance. So the idea behind resonance is that it disperses the negative charge, conferring stability. So classic examples would be comparing the acidity of carboxylic acids and peroxo acids. So on first glance, it does appear that this could be a stronger acid. Why? Because there's more highly electronegative atoms which can stabilize the negative charge better. But let us take a look at the conjugate bases for a moment, and we notice that there is possible resonance stabilization of the conjugate base of the carboxylic acid. Right? This is the resonance we learned. But is it possible for us to have the same resonance? If you try to draw, say you push down this lone pair, and then what happens, right? You can't break this sigma bond over here. Remember, one of our rules is that normally sigma bonds are not broken, right? So there is no good resonance structure that can be drawn, and therefore this is the more stable anion, and carboxylic acids are more stable, are more acidic. Then peroxo acids. So let us take a look at inductive effect, which is also in the H2 syllabus. The clearest example would be with a Cl group. It can withdraw electron density through the bonds via inductive effect, and thus dispersing the negative charge on this oxygen atom, thus stabilizing this anion relative to the other anionic species. The last point, which is fairly important, is orbital. So let us take a look at this phenomenon, which is that alkynes more acidic. Okay, let me write out a sequence. So more acidic on one end and less acidic on the other hand. So on one end, alkynes are more acidic and alkanes are the least acidic. So the reason behind alkynes, which is basically this if you don't remember, and alkenes is somewhere in the middle. Let us take a look at the conjugate bases. Okay, the more stable the conjugate base, the more stable, the more acidic the acid. So we note that in the alkyne molecule, the deprotonated alkyne to be more specific, the negative charge is held in an sp orbital. And note the sp orbital has greater s character. And so what does it mean when the orbital has greater s character? It means that it is closer to the nucleus. As of the same quantum shell, the s orbital is closer to the nucleus than the p orbital. And what does this mean? This means that the negative charge is now closer to the positively charged nucleus. And since opposite charges attract, it is more stabilized. So now let us take a look at the alkene. It is held in a sp2 orbital, greater p character, less stable. And for this one, actually, normally this kind of carbocations rearrange to form a planar configuration such that the negative charge is held in a p orbital, which is even less stable. So there we have it. This explains why alkynes is more acidic, because its conjugate base is the most stable by orbital effect. And so this brings us to the end of our short discussion here about the ARIO rules, and see you for the next video. Thank you.